Let's say there's a piece of wire that's not connected to any electrical circuit, so there's no difference in electric potential between one end of the wire and the other. In fact, there's no voltage applied whatsoever. Now let's say that the total net charge is equal to 0. So all the electrons you see here don't represent some net amount of charge. There would be some atoms, and the nuclei we know are positively charged, and if that atom is lacking in one electron, then the whole atom itself is positive. So for every free electron, there's an atom that's lacking an electron and it's positively charged. Although I don't really want to show the positive charges because the atoms are pretty well locked in place. The electrons are the ones that are free to move, and they move about with random velocities. So this electron might be going in that direction. This electron might be going here. If I were to draw a bunch of velocity vectors, no two vectors are going to have the same length because the speeds of all these electrons are not uniform. So they're vibrating about, and they collide either with other electrons or with other atoms, and they bounce around. So maybe the path for one electron might look like this. Moves in this direction, collides, and then moves this way, collides with something, and moves this way. Statistically, over time, that electron is going to have a net zero displacement. And this is true of all the electrons. They might vibrate about, but they don't work their way together all to the left or all to the right through this wire. They're basically vibrating around some origin and have no net displacement over time. Now, if we do connect this wire in an electrical circuit, and maybe we make this end of the wire low electric potential and this end is the high electric potential, then these electrons bounce around and undergo collisions, and because this is the high potential and this is the low potential, that makes an electric field that points to the left. Now, I'm not going to draw the electric field lines inside of the wire. Well, maybe I change my mind. I suppose I can. No harm in that. So the electric field points like this. And you might say, wait a minute, I thought conductors have zero electric field inside. But if you watch my last video lesson, I pointed out that that's only true for conductors in electrostatic equilibrium, but the potential difference across the ends of this wire do not allow it to reach an electrostatic equilibrium. So the electric field is definitely not equal to zero. It points to the left throughout this wire. And that causes the electrons to experience a force. And now electrons being negatively charged experience a force opposite the direction of the electric field. And so the electron doesn't just travel in a straight line from one end of the wire to the other, because the electrons undergo collisions and bounce around. So we can see the path taken overall by the electron as it bounces around. Ultimately, there's a net displacement from one end of the wire to the other. It takes a long time for the electron to travel. The drift speed indicated here, if we were to take the length of the wire, L, and divide it by some amount of time that it takes for the electron to go from one end to the other, then that would represent the drift speed. And that drift speed is on the order of about 10 to the negative fourth meters per second. So this is really slow, right? Think of it like the pace at which a snail crawls. So that's the idea. The drift speed is opposite the direction of the electric field in the case of electrons that have a charge that's negative. Now, there are some semiconducting materials, right? Materials like silicon or germanium. So unlike metal, there are some conductors for which the charge carriers are positive instead of negative. Electrons aren't the only possible charge carriers for conductors. And then if you had a high potential and a low potential, then these positive charges would collide and bounce around, but overall have a net drift in the direction of the electric field. So for electrons, once again, review, the electric field points from high potential to low potential, and the drift speed is opposite the direction of that electric field. If you had a semiconductor, and there are p-type semiconductors and there are n-type semiconductors. P-type have positive charges as the particles that drift when the electric field is applied. N-type semiconductors, you guessed, are negative type, where once again it's a negative charge. So let's say this represents a p-type semiconductor. Electric field points from high potential to low potential, and the drift speed is in the same direction. We're actually not going to talk a whole lot about semiconductors. Most of our conversation about the conduction of electricity will involve metal, wires. And in that case, electrons are the charge carriers, and their drift speed is always opposite the direction of the electric field. And that drift speed is on the order of magnitude of about 10 to the negative fourth meters per second.